Hi guys, this is topic 8.5, acid-base titrations. Excuse me. So the objective today is to be able to explain results from a titration of a mono or polyprotic acid or base solution in relation to properties of the solution and its components. So a couple key terms you need to be aware of. Titration is one, monoprotic, polyprotic, what else? Equivalence point. So we've kind of we did titrations a little bit. We did like a lab online where you were doing it for like the whatchamacallit, like for like the effects on a river or something like that. So yeah, so this is pretty much that, but just getting a little bit more detail. So an acid-base reaction can be carried out under controlled conditions in a titration. What a titration is used for, it's a way to analyze acid-base reactions. Typically, you have a known concentration of a base and it's added to some unknown concentration of an acid or the opposite. You measure the volume of both solutions and it's used to calculate the unknown concentration. The solution with the known concentration is known as a titrant, and the thing that you're trying to analyze or you're trying to find out about is called the analyte, which kind of makes sense, I guess. So in this diagram, so what's happening is you have a base with a known concentration and you add it to an Erlenmeyer flask. That's the one on the bottom. It contains the flask itself contains some acid. It has an unknown concentration, but we know that it's at 25 milliliters. The volume of the base, so whatever you are titrating, is found by reading the volume on the burette. For example, the volume transferred to the flask is 26.27 milliliters. And if you know what the concentration is, you can then calculate the concentration of the acid in the burette with this type of titration because you're reaching something called the equivalence point. And you use an indicator for that. Indicator will change color when it becomes an acid or becomes a base, etc. So at this equivalence point, whatever that volume is, etc., you can figure out what the molarity is. So for example, for this one, we know that the molarity of the base NaOH was 0.1010 molar. The volume that was added was 26.27 mLs. And from there you get your number of moles. Assuming that this is now because we're at the equivalence point, we can assume that the moles of the base equals the moles of the acid, and from there you're going to divide by the volume of the acid that was in the Erlenmeyer flask originally, and from there you would get your molarity. A titration curve can then be constructed by plotting out the pH against the volume titrant added. The titration curve is useful for summarizing results, and from there you should be able to recognize what type of acid or base is being added, etc. You can tell by the strength of it by the curve itself. So that's something you should be able to recognize. Sorry about that one. So you have your strong acid titrating with the strong base. And you know you're starting off with an acid because look at where your pH, the bottom of the initial part of your graph is starting off at a lower pH. That means you have an acid that you're adding a strong NaOH, a strong base to. Because they're both strong, the pH will be at 7. And this is the point at which we have equal moles of the strong acid and the strong base as well. When looking at the graph, we will look at the sharpest slope, and that will correspond to the equivalence point. So the middle part of that should be the point where you have equal moles, and that should be where your pH is. pH should be 7 for a strong acid and a strong base. So you may need to look here. Let me see. Where's my pen right there? So the equivalence volume. So 25 mLs. You have your equal moles at a pH of 7 there. So by knowing that this volume right here, 25 mLs, you're going to use that with your sort of like it's not a dilute. I guess it's a dilution. M1V1 equals M2V2, but it's the moles of the hydronium ion times the volume of the hydronium ion equals moles of hydroxide times the volume of hydroxide. So now we have a weak acid titrated with a strong base. So here, your weak acid is called potassium hydrogen phthalate, phthalate KHP. It's being titrated with a strong base NaOH. So the curve itself is kind of similar to the original one for the, not really for the most part, but you can tell there's a similarity. But there are a few major differences. We are still going to determine the steepest point, the inflection point of our curve, to determine the equivalence volume. So when you see, though, that when you are titrating a weak acid with a strong base, your equivalence point is above a pH of 7. Because as the weak acid is neutralized, its conjugate base is formed, causing the solution to be basic in a sense. We can also use this titration curve to determine the pKa, or the negative log of the weak acid. The pKa, this is important, the pKa is equal to the pH at half the equivalence point. This is true because at this halfway point, there are equal concentrations of the conjugate base and acid. And because half of the initial concentration will be neutralized, and you will have formed the conjugate base. The last thing to note is that with this graph, there's a section about 15 to 25 mLs added where the pH doesn't change much, and this is called a buffering region. So we're going to talk about this in a later unit, buffering. So you should be, if you're going to take away, well, you got to take away a lot from this, but take away how to determine the pKa of a weak acid. That's probably something you should be paying attention to, at the very least on this slide. If we're looking at titrations with polyprotic acid, so multiple ions, multiple hydrogens, we can tell that it's diprotic because there are two inflection points where you have, when I say inflection point, remember that is the point where the slope appears to be at its steepest. These correspond to when the two protons are being donated. And from here, we can determine the pKa of each of the protons by getting half the equivalence point. So if this was my pH here, if I do the halfway, the equivalence point about there, that will give me my pK values for those particular things. Two protons are being donated. They're going to be donated in an order, not necessarily at the same time. And this you can tell because you have different pKa values for this. So you should be able to recognize, hopefully, the pKa values of polyprotic acids, or even just like a weak acid and a strong base type of thing. Something that you don't have to worry about on the AP exam is determining the concentration of each species present in a polyprotic titration. They won't do that to you, but you should be able to do it at least for just when it's only a monoprotic or just one hydrogen that's being donated. So you have a strong acid and a strong base. Estimate the equivalence point and determine the concentration of the HCl. If you're titrating 20 mLs of HCl with 0.121 molar NaOH. So here's the first step. One, you have to recognize what is the actual reaction itself. So you can probably use multiple ratio type of thing. So you have HCl, aqueous, plus NaOH, aqueous, produces NaCl, aqueous, plus H2O, water. Looking at this, it probably won't be as nice for you on the test, but this says the equivalence point is at 25 milliliters. So that means I'm adding 25 mLs of NaOH to reach here. So that's what I'm going to start off with. 25 mLs NaOH over 1. So then I'm going to, because I'm titrating, I'm just going to use this right here. So this is going to be 0.121 moles NaOH over 1,000 mLs NaOH. So I don't have to worry about converting this from milliliters to liters. I'm doing this here in my one step, or I guess 2 steps. So to find the concentration of HCl, what I need to do now is convert these moles to NaOH using my using my mole to mole ratio. So 1 mole of NaOH, and then this is 1 mole of HCl. This will equal, let's see, I'm trying to give myself a lot of numbers, before I finish my answer type of deal. So 0.003025 moles of HCl. Oops. It's ugly. So I want to find the molarity of my HCl. So I'm going to take my moles that I attained and divide that by the volume of my HCl that I started off with. So it's going to be 0.003025 moles of HCl over 0.0200 liters of HCl. And that will be 0.15 molar HCl. So the graph below shows the titration of oxalic acid with sodium hydroxide, NaOH. Label the equivalence point, estimate the pH at the equivalence point, and estimate the pKa here. Use a different color. So first, find the equivalence point. So it looks like it's about, it's about at 30 mLs of NaOH. And it's about halfway here. It looks like it's a little bit above 8. So this is my equivalence point. My pH is about, let's say, it's about 8.5-ish. And estimate the pH, estimate the pKa of the oxalic acid. So halfway at the equivalence point right here, so it's about 15. So I go across here and I obtain the pH at halfway at the equivalence point. So that means my pKa is 2.5. All right, so that's it for now. Let me know if you have any questions. Thanks.